Good day, good people. Let us look at this vector kinematic, but using the vector method. Okay, look at it, but using the vector method. Firstly, let's start with the resolving method. The method that it's a vector method, but the understanding that we have of it, it is, let's say we are having um, two forces. We are having a force on the 45 degrees, then we are having one heading south. Let's say this one, it is 130 kilometers per hour, and this one, it is 120 kilometers per hour. Now we then have to resolve this force to be either vertical or horizontal, because the method that we are using, it has to do with vertical components and horizontal components. If we were to resolve it to be either vertical or horizontal, we would then say this force, it is opposite over hypotenuse. That means the vertical force here, it will be 120 sine 45. Then the horizontal one would be adjacent over. It means the horizontal component, it is taken from the cos. Then it will be 120 cos 45. Now check, it is heading east, right? This one, it is equal to that one, it is heading east. Now in calculating the vertical component, then it will be vertical component equals to, we look for vertical component. We are having two vertical component, we are having this one and that one. We are having 120 sine 45, it is positive, it's going up. This one, it's a negative force, it's going down, it's 130. Then we get our answer as 120 sine 45 plus minus 130. Then we get our answer as negative, vertical component as negative 45, 147 kilometers per hour. Now, same method, but same method in a different way. Now, this is the method, this is another way of looking at it. We know that vertical component, it is made up of what? Of sine. You are having your triangle, you are having your angle there. We know that opposite over hypotenuse, that would be your sine. That means vertical component, it is made up of what? Of sine. Then when we want to calculate the horizontal component, this would be your vertical component. In calculating your horizontal component, it would be adjacent over hypotenuse. That means horizontal component, it is made up of what? Of cos. Okay. Now, same method, but we'll be using it in this way. Now, the method that we'll be using, you are looking for forces, the magnitude of a force and its position. Now, you always start at zero when you look for forces. This is where I will start to look for what? For my vectors on that vector diagram. Now, boom, I found my first force, its magnitude. I'm looking for vertical component. Vertical component, it is made up of sine, as I've explained here. Horizontal component, it is made up of cos. It means if I'm looking for vertical component, I'll be working with sine throughout. Okay. Now, I found my first force. It is 120 sine 45. That would be the magnitude and the position. Plus, you start all over again from zero. Boom. I found my second force. It is 130. Position, it will be sine 270. Now, you'd realize that the answer would be the same. 120 sine 45 plus 130 sine 270. The answer would be the same. It is negative 45, 147 kilometers per hour. Now, on this method here, if you are calculating for vertical component, you look for if you are looking for the vectors, the magnitude of the vector and its position, then you add all of them. You add all of them, since all you are looking for what, for vertical component, and we know that vertical component, it is made up of what, of sine. Okay, then we know that in looking for horizontal component, it is made up of what, of cos. That means where the sine, we put what, cos. It will be 120 cos 45 plus 130 cos 270. Then you get your answer. Here on this one, we only have, on the horizontal component, the only horizontal component we have is this one. It will be 120 cos 45. What's your answer there? Let's see. 120 cos 45. Then we get our answer as 84,853 kilometers per hour. Now, coming to this one as well, you'd realize that your answer would be the same. 120 cos 45 plus 130 cos 270. Your answer is exactly the same. It is 84,8 is it 853 kilometers per hour, would be the same. Now, it's up to you if you want to use the resolving method, or you want to use what I normally call vector method. Okay, now let's do the application of this on this equations here. Okay, a two-speed boat leaves Port Elizabeth Harbor simultaneously. Boat Q travels south. Then you make your Cartesian plate north, east, south, west. It is heading south. That would be boat Q. VQ, it is heading south at what speed? 104 kilometers per hour. Then boat P travels southwest. South is your reference point, west. That means it's 45, 45. Like I always say, our quads are made up of 90. Whenever you project or you plot your vector diagram, work from the 90 perspective. It will be easy for you. Then this is VP at what speed? 127 kilometers per hour. Now, we've managed to draw the given information into this vector diagram. Now let's go and read the question. What is it that they want us to calculate? Calculate the velocity of both Q. Calculate the velocity of both Q relative to. Now, whenever you are given this statement here, calculate the velocity of both Q relative to, you will keep VQ in its position and reverse VP, the velocity of both P in magnitude and direction. Now, you will keep VQ in its position and reverse what? VP. That's what I call stop and reverse. Now, you will then have to redraw this from the stop and reverse perspective. Now, we know that VQ, it is heading south. We said it that we will keep it in its position, 104 kilometers per hour. This is south, this is east, north, west. Then we will reverse VP. VP, it is now heading the opposite direction. At what speed? 127 kilometers per hour. 45, 45. Now, we know that east, it is at 0, 90, north 90, west 180, south 270, then the revolution it is completed. Now in calculating the resultant, we will be using the vector method, the one that I've just introduced now, or the resolving method. Now we are looking for forces, we are looking for vectors, the magnitude of the vector and its position. We will start at 0, boom. We found our first vector. In calculating the vertical component, it will be sum of the vertical component equals to, we found it, it is 127. Its position, it will be sine 45. The fact that we are looking for vertical component, then it will be plus. You start all over again, you look for the second vector, 90, 180, 270, boom. We found our second vector. The magnitude, it is 104. Position, it is sine 270. Then you calculate the vertical component. Then in calculating the vertical component, I got negative 14,197 kilometers per hour. Now, when coming to horizontal component, where the sign you put cos, you write everything as it is, but where the sign you put cos, then it will be 127 cos 45 plus 104 cos 270. Then I got my answer as 89,803 kilometers per hour. Now, in calculating the resultant, then you will be using the Pythagoras. It will be v squared plus horizontal component squared, all square root. Our vertical component, it is 14,197 squared. Horizontal component, it is 89,803 squared, all square root. Then I got my answer as 90,918 kilometers per hour. Boom. This is how easy this method is. Then when coming to direction, since well they said we should calculate the magnitude and its direction. Now when coming to the direction, you will then plot your vector diagram. But we know that all forces going up, they are positive. All forces going towards the east, they are positive. All forces going towards south, negative. West, negative. Then you look for the coefficient of your vector component and your horizontal component. They will indicate to you the position of your resultant. Now, when I look at my vertical component, I have a negative answer. It means my vertical component, it is heading south. It is negative 14, right, comma 197 kilometers per hour. I've already indicated that it's heading south. The direction, it is south. It means it's a, it's a negative. Negative in this case, it indicates the direction. Okay. Then the horizontal component, it is positive. We've got the positive invisible sign there. It means it's heading what? East. It is 89,803. That means this is where my resultant would be. Now, it's up to you if you calculate alpha or theta, it doesn't matter. Now, in calculating the direction, let's wipe here. In calculating the direction, you will then use trigonometrical function, but in this case, we will be using tan. Whether you calculate a theta or alpha, it doesn't matter. It doesn't matter. Now, it will be tan alpha. Let's calculate tan alpha. It is opposite over adjacent, okay? Or we can calculate it is opposite over adjacent. It means it is horizontal component over vertical component. Then alpha would be the inverse of tan. Horizontal component, it is 89,803 divided by 14,197. Then we get our answer as the inverse of tan 89,803 divided by 14,197. 197. I got my I get my answer as 81 comma 81 comma 016 016 degrees. Now we know that our quads are made up of 90. Then in calculating the theta, it will be 90 minus, that 81. 90 minus that 81, then we get our answer as, okay, minus 90. Then I got my angle there as 8 comma 983 degrees. Then we go back to the given principle. The given principle says you start with the cardinal closest to your vector first. Between the two, you can tell that from here to there, it is 8, 983. Then from here to there, it is 81, 016. That means our resultant, it is close to east. And writing the direction, it will be east 8, 983 degrees south. Or even if you write it this way, they will not falter you. You will get full marks. It will be south as your reference point. South 81,016 degrees east. You will still be given full marks because our quads are made up of 90. Now you are within the 90 of this quad, fourth quad. Hence the direction, it is south. 81,016 east, or it is east 8,983 degrees south. This quad. Right. This is how you apply this method. We've then managed to calculate the resultant. Therefore, the resultant is 90,918 kilometers per hour at east 8,983 degrees south. They will not falter you if you said or south as your reference point 81,016 degrees east. You will still get full marks. Right. This is how we apply that method on relative motion. Relative motion, we stop and reverse. Now let's look at the resultant. The resultant, we are given the statement here: a light aircraft with airspeed of 300 kilometers takes off at OR Tambo Airport in a direction. Now we need to project the given information into a vector. This is north, east, south, west. Now south is our reference point. South 33, south 33 degrees. Then we know that 90 minus 33 equals to 57. That means here it is what? It is 57. Like I said, that our quads are made up of what? Of 90. Because when you add the 33 and the 57 there, they must give you the 90 degrees because our quads are made up of what? Of 90. Let me charge my laptop before it fails me. Just a minute. Now this is what we've projected. This is the SP, the light aircraft, VA at what speed? 300 kilometers per hour. Then we are told the aircraft is blown off course by heavy wind blowing at 138 kilometers per hour from a direction. From a direction. That means the wind it is blowing north, it's your reference point. North, the wind it is blowing from this quad, heading what? The opposite quad. North, it's your reference point. This is 49. That means this is 41. North, it's your reference point. The angle of deviation, it is 49. North, 49 degrees west. It is from, where is it going? It is going to southeast. It is going this direction here. This is where the wind is going. V wind at what speed? 138 kilometers per hour. This it is opposite to that one. This would be 49 degrees. That means this would be opposite to that one. It will be 41 degrees. That's what we have projected. They never said calculate this one relative to. Now we don't stop and reverse on this one. We are looking for resultant. We don't stop and reverse. Now, in using the vector method, when we are determining vertical component, we will be looking for those vectors in this diagram. We will be looking for their magnitude and their direction. But we always start at 0 degrees in looking for those vectors. We start from what? From 0 degrees. Now, I will start from 0 looking for those vectors. 0, 90, 180. Boom. I found my my first force there. It is 180 plus 57. Right. I found it. Its magnitude, it is 300. Its position, it is sine. It is 180 plus 57. Then it will give it gives me 237. Now the position of this vector, it is sine 237. The magnitude, it is 300 plus. Then you start all over again. You look for another one. 90, 180, 270 plus 49. 270 plus 49 equals to 319. I found my second vector. The magnitude, it is 138. Its position, it is sine 319. Like I said, if you are looking for vertical component, you will be putting sine throughout. I don't care if the vector is on the horizontal line or what, you put sine because your vertical component, it is made up of what? Of sine there. I hope that makes sense. Then I get my vertical component as negative 342, 137 kilometers per hour. Now, where there's a sign in calculating the horizontal component, you put what? Cos. It will be 300 cos 237 plus 138 cos 319. Then I got my horizontal component, the value of horizontal component as negative 59,242 kilometers per hour. Then in calculating the resultant, it will be vertical component plus horizontal component, all square root. We use the Pythagoras. Then it is 342,137 squared plus 59,242 squared, all square root. Then I got my answer as 347,228 kilometers per hour. Then when coming to the direction or the position of your resultant, the coefficient of your vertical component and your horizontal component will indicate for you the position of your resultant. Now, in this case, I have a negative vertical component and I've got a negative horizontal component. Then you go back to your Cartesian plate. We know that all forces going up are positive, east positive, south negative, west negative. That means this is where my resultant is. Based on the coefficients, that means my resultant, it lies on the third quad. I'm having a horizontal component, it is negative, it is heading west, and it is 59,242. Then I'm having a vertical component, it is heading south, it is 342,137. Whether you calculate alpha or theta, you will use the principle. You start with the cardinal closest to your vector first, then the angle of deviation, then the other cardinal point. Then in calculating this one, we'll just save time. We'll calculate theta. Then it will be theta equals to the inverse of tan 59,242 divided by 342. Then we get our answer as the inverse of tan. It is 59,242 divided by 342,137. Right. I got my answer as 9,824 degrees. That means my resultant, it is close to south. Now in writing the direction, it will be south 9,824 degrees west. Or if we've calculated the alpha, it will be west 80,176 degrees. What? West. Because when you add this and that, you must get what? 90. Now our resultant, it's on the third quad. Whether you write your direction as that or as that, it doesn't matter. Your answer will be the same and the correct one. Now let's do this one using the cosine rule. Let's do this one using the cosine rule and see if we won't get the same answers. Okay, let's wipe so as to apply the cosine rule and see if the answers won't be the same. The beauty about the kinematic is that you can always use all the given methods to prove your answer. But I always prefer the vector method. You will not go wrong. This vertical component method, you will not go wrong. You will always be correct. Right. Now let's use the cosine rule. A light aircraft with a speed of 300 takes off at OR Tambo in the direction. Now let's write it. Let's project. This is north. This is east, south, west. It is heading south. South is your reference point. Angle of deviation, it is 33. That means here it is 57 degrees. Right. At what speed? VA, it is at 300 kilometers per hour. Then there's a wind blowing. Now in projecting the direction of the wind, let's write this one a bit top up. It is 300 kilometers per hour. In projecting the direction of the wind, you will project it at the head of the plane, meaning at the tip of that arrow. They are saying the aircraft is blown off course by a heavy wind blowing at 138 kilometers from a direction north. You make your second Cartesian plate. This is north, east, south, west. From north is your reference point. It is blowing from. It is 49. This would be 51. Blowing from to this direction there. V wind, it is 138 kilometers per hour. Then we must complete this with the mirror image using the parallelogram. Parallelogram said this side must be the same. Two sides must be the same and equal. If it is heading that direction, this one it is heading that direction. Then this one it is heading. Then I'm having head to head. I'm having tail to tail. This is where my resultant would be. Now, as soon as you see head to head, tail to tail, it is the indication of the position of your resultant. I will denote this as my A, denote this one as my B, denote this one as my C. Then this would be my small a this would be my small b, this would be my small c. Now in using the cosine rule, I'm looking for the small b. This is the resultant that I'm looking for. It is a squared plus c squared minus 2ac cos beta. I then have to determine this angle. If this is 49, this is 41. Now this alternates with that one. I'm having 57. Now 47 plus 41, I get my answer as 98 degrees. I've managed to determine that angle. Now my a, small a, it is 138 squared. My c would be 300 squared minus 2 times 138 times 300 cos 98. All square root. Then I get my answer. In determining that, I get my answer as 347. 347,228 kilometers per hour. It doesn't matter whether you use that vector method or you use the cosine, your answer would be the same and the correct one. Now, when coming to direction, please make note, you always calculate the angle of where you have started drawing your vector diagram. Where did we start drawing our vector diagram? Here. That means this is the angle that we are looking for. We are looking for big A. If we are looking for a big A, then we'll be using the sine rule. Then it is sine A over A equals to sine B over B. We are looking for A. It will be A equals to the inverse of sine, open bracket. The A, it is 138 sine 98 divided by what we have calculated, 347,228. Then our angle would be the inverse of sine 138 sine 98 divided by 347,228 close bracket. Then I get my answer as 23,177 degrees. Now check this. This angle that I got here, it is this one. But we then need to ask ourselves, this is your resultant. Check where your resultant is. It made a smaller nyana gap there. Now, this 23 occurred within the 33 angle that was given. Okay? It occurred within this 33. Now, we then have to get that smaller nyana angle. Remember, from here to this cardinal point, we need to get 33. But this time around, we've calculated the angle, and the angle that we got from here to the resultant, it is 23. Then we need to calculate that smaller nyana angle there. What is its value? Then you would say 33 minus 23,177. Then you get your answer as well as 9, I got my answer as 9,823 degrees. Now, then you go back to the given principle. Your resultant, it is close to which cardinal? Is it close? This is where your resultant is. Is this resultant close to west? If it is close to west, remember, it has to be 23,177 plus 57. Then you get your angle there as 80,177 degrees. But the principle says you start with the cardinal close. But we know that from here to where the resultant is, it is 9, it means it will be south 9,823 degrees west. Or you can say west as your reference point, 80,177 degrees south. Is it not the same answers as we got when we were using the vector method? This is how you determine your kinematic. I don't care what question they will give you. If you would use the vector method or the cosine rule, it doesn't matter. Your answers would be the same and the correct one. Thank you, good people.